All right, so today we're going to learn about binary numbers. So we'll first begin with the definition of what binary numbers are. So within the name, we have bi, which means two, and the numbers. So two numbers. And in this case, the two numbers are 0 and 1. And the reason why binary numbers are so important today is because of pretty much transistors. Transistors define our modern era today is because we could fit so many of them in a small area, such as a phone or a computer. And although transistors can only hold a on or off state, so just two states, they're so important and useful because of how much we could store in a small area because they're so tiny. They're on the scale of nanometers or I think even picometers today. So, what can we do with binary numbers? So, there are pretty much two main things that we could do with it. So, Boolean logic is one of them. And what Boolean logic is just logic that deals with two things, true or false. And since binary numbers have 0 and 1, just two things, and Boolean logic just have two things as well, we could map it together. So, for example, 0 can be mapped to false, while 1 can be mapped to true. And this is not the only mapping, of course. Another mapping could just be 0 is true and 1 is false. It doesn't matter which way you do it, as long as you're consistent throughout the whole thing. So then another one is to create a number system. So binary numbers could be used to create a number system. So what is a number system? So I think the easiest way to start with that is the decimal number system. So decimal. So all of you guys are familiar with this for sure because the decimal number system is the one that we use every day. So 0, 1, 2, 3, 4, 5, 6, 7, 8, and then 9. So then the reason why it's called decimal is because we only have 10 symbols to work with. And with these 10 symbols, we have to create an entire number system with it. And how we do that is, let's say we start at 0. If we were to add 1, we go to 1. If we were to add 1 again, we go to 2. And then if we add another 1, we go to 3. And then if we keep going, we eventually end up at 9. But what do we do after 9? We don't have another symbol to represent what happens after 9. So what we created is that once we reach 9, to go to the next number, if we add by 1, we have to then go to the next digit. So then we go to 1 and then 0. And this 1 represents that we reached 10 in the last digit, which is this digit. So then if we keep adding 1 again, we get 11, since this is the 1's digit. And then if we keep going, we'll eventually reach 19. And then if we add another 1 to 19, there's no symbol to represent what happens after 9. So then we have to add 1 to this digit. So then it goes to 2 and then 0. And then you just keep doing this. And then eventually you reach 99. And then if we were to add 1 to 99, there's nothing to represent what happens after 9 in the 1's digit. So then we have to go to 0 here and then add 9 by 1. But same thing here. There's nothing to represent what happens there. So then we have to go to 0 and then we do 1 here. So then it's 100, which is 100. So that was the decimal number system. So now if we were to make a binary number system, we only have two symbols to work with instead of 10. So the two symbols are 0 and 1. 2 symbols. So then now we have to create an entire number system out of just 2 symbols. But the same rule applies with what we did with the decimals. So if we start at 0, if we add by 1, we get a 1. But then if we add by 1 again, we don't have a symbol to represent what happens after 1. So if we're at 1, and then we add by 1 again, since there's nothing to represent what happens after 1, we have to go to the next digit, which is 1 and then 0. And then if we add this by 1, we get 1, 1. And then if we add 1, 1 by 1, since there's nothing to represent what happens after here, we go to 0. And then we have to add this digit by 1, but there's nothing to represent that either. So 0, and get 1, 0, 0. And this represents the decimal number 4. Because if we were to add all the times that we add 1 to this, we begin with 1, which is already 1, and then we add another 1, so 2, 3, and then 4. So although this looks like 100 in the binary number system, in the decimal number system, in the binary number system, it's actually just 4, since we only had 2 symbols to work with. And the reason why we create number systems like this, because we can't memorize as humans 1,000 symbols. We can only memorize a few. So that's why the one that we use every day is the decimal. We memorize just 10 symbols, but there's a whole system behind the 10 symbols that allows us to go up to an infinite amount of numbers without having to memorize an infinite amount of unique symbols for it. So if you keep going down just engineering in general, you will most likely hear the hexadecimal number system. And the hexadecimal number system is pretty much the same as the decimal and the binary, except now there are 16 symbols. So 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and then for 10, they represent it as A, B, C, D, E, and then F. So this is how the hexadecimal number system works. 16 symbols. But the rules are the same thing. If we reach F, if we add by 1, we get 1, 0. But instead of this representing 10 in decimal or 2 in binary, in hexadecimal, this represents 16, since we went all the way from 0 to F, and then we added by 1 again. So yeah, this represents 16 in decimal. But so yeah, decimal, this is what it represents. But then in hexadecimal, this is what it represents. Yeah, hexadecimal. All right, so the last thing I want to talk about is how to quickly compute the values in each number system. So the easiest way to start with this is just with the decimal number system. So if I were to give you a number like 938, how can we create a system to find the value of this? Of course, I know all of you guys know the value of 938. It's 938. But let's just create a system on how to do this. So with the first digit here, this is the ones place. So first we have to create a system of how to differentiate between each of these digits. So what we could do is we could do a 10 and then to the power of what? So in this case, it should be to the power of 0, since 10 to the power of 0 is 1. So we get the ones digit here. So yeah, so here, this is the same thing as 1, right? So yeah, this represents the ones digit. So then now, how do we represent how many of each of those things are in that digit? So in this case, how many things are in the ones digit? There's 8 things in the ones digit. So then we have to have an 8 in front. So then now we do 8 times, 8 times whatever thing is in that digit. And here, this represents the digits place that we're at. So we're at the ones digit, and then this represents how many things are in that digits place. So then now if we go to the tens place, we do the same thing. So then how do we represent the tens place? We do 10 to the power of 1, since 10 to the power of 1 is 10. And how many things are in the tens place? There's 3 things. So 3 times 10. So then here we get 8, and then here we get, sorry, that 8 does not look good. So 8, and then here we get 30. And then, yeah, the same thing goes for 9. So what digits is this in? It's in the hundreds. So 10 to the power of 2 is 100. And how many is in there? So 9. So we get 900. Yeah, so then to compute the entire value of this, we just add these values up. So then in the ones place, we have 8. In the tens, we have 30. And then in the hundreds, we have 900. So it's 938. And of course, that seems very trivial in the decimal number system. But now let's say that we use the binary number system. So we'll start with just 4 digits. So then 1, 0, 1, 1, for example. So how do we compute the value of this? So the way that we do that is we start with the ones place. So in the ones place, we have instead of being 10, right? Since there's 10 symbols in the decimal, we only have 2 symbols in the binary. So then we do 2 instead. So then 2 to the power of 0 is 1. So then now how many are in the ones place? There's 1. So 1 times 1 is equal to 1. And here comes the main difference between binary and decimal. Instead of this being the tens place, this digit here does not represent 10 of this digit, right? Because we don't need to add 10 symbols to get this 1 here. All we need to add is another 1. So yeah, if we add, for example, this last digit by 1, we get a 1 here, right? Because 1 plus 1, 1, 0. So instead of calling this the tens place, we call this actually the twos place. Or I don't know if it's actually called the twos place, but that's a way to think about it, right? Because how many times did we add 1? We added 2 times. So this 1 here represents that we have added 1 2 times. So yeah, that's why there's actually a 2 here, right? And how many? So sorry. So yeah, 2 to the 1. To represent the twos place. And how many are in the twos place? There's 1. So that's why we get 2. And then for 0, in this place, we have, this is now the 4's place, since it's 2 to the 2. And how many are in here? It's 0. So 0 times 4 is 0. And the reason why this is because if we keep going up here, right, if we add this by 1 again, we get 1, 1. And then if we add 1, 1 by 1, then we get, 1, 0, 0. And how many 1s did we add in total? There's 1 here, 2, 3, 4. So then that's how we got it here. Yeah. Each one of these digits just represents that we have added 2 to the last digit, right? So to get 1 here, we had to add 2 here. To get 1 here, we have to get 2 here. To get 1 here, we have to get 2 here. And that pretty much is how we get to this system. So the last digit, 2 to the 3. How many are in here? There's 1. And we get 8. So the total value here is 8 plus 2 plus 1, which is equal to 11 in decimal, of course. 1, 1 in binary would be 3, but in decimal, 1, 1 is 11. So yeah, we could do this with any number system. So as long as you know what the number system is. So in this case, we define this as the the binary number system. But if I instead asked you to find what is the value of this in the hexadecimal number system, you would do the same thing. So instead of this being 2, this would then now, let me change colors. This would then now be 16, since there's 16 symbols, right? Yeah, so all the numbers here would then change, on the bottom would change to 16. So, okay, sorry. Let me just erase this real quick. And yeah, so then now it would be 1 times 16 to the 0, which is 1, since 16 to the 0 is 1. And then 1 times 16 to the 1, which is 16. And then 0 times 16 to the 2, which is 0. And then 1 times 16 to the 3, which is, I actually don't know what this is, but you get the point. I could change this number to be, for example, like 3, 4, AF, right? Since in hexadecimal we could go all the way up to F. Yeah, and then these numbers would then change. Only thing that would change is the numbers in front, since the numbers in front represent how many we have at each digit. So in the first digit, which is this line here, we have an F instead of 1. So this would then be an F. I think it would be easier if I changed colors. Okay. Yeah, this would then be an F. And then the next digit, which is this line here, we have A. And then, yeah, if we just keep going, yeah. So yeah, that's a system on how to compute in any number system. I hope that makes sense, and I hope this video helped. Thank you.